independently from the same distribution and apply it. And just keep on repeating that. And at time n, you'll end up at some point that I'm going to call f to the n omega of x, where I think of omega as some sequence of symbols that encodes the random itinerary that's being followed. So you can think of omega as an element in diff m to the n, so sequences of diffeomorphisms in here, where omega is distributed according to the product measure of mu with itself, countably many times. So this is IID Bernoulli dynamics, so probably what you would guess to write down, but I just want to introduce this just so if I write omega later, it's been introduced. So here's the setup, but what am I really interested in? What I'm really interested in are, like, what are good criteria for these random dynamics to have strong chaotic properties. So somehow, what we'd like is we expect that if you have, a bunch of random diffeomorphisms that you're multiplying together, they probably should be kind of chaotic, but what we'd like is a way to tell that they're going to be chaotic that is kind of robust and also is checkable in particular cases. So what I want to start with is discussing the case of surfaces. So let's consider now the case where M is a surface. Okay? And in this case, I'm just going to tell you a criterion that I think works pretty well. So in this case, here's a definition. So we'll say that a measure mu on is expanding on average. I put the 2 on M just to emphasize it's a surface. If the following condition holds. Now the condition's a little technical looking, so let me say it. So what is it going to say? It's going to say that there exists some finite number of iterates of the system that you consider, and some positive number c, such that we then have the kind of very uniform statement on how much a tangent vector to the manifold gets expanded. So then, for all points x in the surface, and all unit tangent vectors at x, we have the following inequality. When we look at the expected length under the nth iterate of the dynamics of this vector, this will be at least c, which is itself at least 0. Okay, so let me pause for a second and go through the definition again. So our criterion is called expanding on average. Maybe we could abbreviate it EOA. And what it says is you look at your random dynamics and you look at some particular fixed time in the future, maybe 100 iterates of the random dynamics. And at that time, you look at a particular unit tangent vector. And you look at all of its images under the random dynamics, and you see how much longer did this thing get, right? Like how much did it get stretched during those 100 iterates, and you take the average.
So that's a big N.
Yes.
After the big N, right?
Oh, yes. Yes, sorry, yes. Sorry, yes, a big N. You just look at time N, just the big N, and you look at how long this vector has gotten, and what you'll see, if it's expanding on average, is that that vector on average is like a factor of 2, for instance, longer. So that's what the definition says. So it's kind of a very uniform condition because it's completely uniform in the point x. You get this expectation wherever you started off with, wherever you started. So one way that I think is how I like to think about the condition is it says that the length of this vector, or like the log of its length, is like a submartingale, right? As you watch the system evolve, the length will go up in expectation, right? And if it's gotten long at some point, it'll keep getting longer. So that provides a kind of very strong kind of hyperbolicity kind of in average. So now I'm putting this forward to you as maybe a good criterion for random dynamics to have strong chaotic properties. So perhaps one of the first requirements a good criterion should have is that there are actually examples satisfying it. So perhaps one of the simplest examples, and one that Davi mentioned yesterday, I guess all the mathematical content of the example, I think, is basically due to Furstenberg. Consider this driving measure. We're going to have two matrices, A and B, and we're going to choose each of them to apply with equal probability to the torus. So A is like this, and B is like this. Right? Davi considered the same matrices, and at each time step we choose one with equal probability to apply. And essentially, Furstenberg, he wasn't studying random dynamics on surfaces when he proved this, but they are expanding on average. Now, a second thing that I said would be desirable for random dynamics is that whatever criterion that gives you some good property should also be robust. So let me add a note here. So this condition here is stable. And what do I mean by that? If we started with our pair of diffeomorphisms given by A and B acting linearly on the torus, and we take a C1 small perturbation, and we get a new pair of diffeomorphisms F and G, then the random dynamics of this tuple is also expanding on average. Then delta F is expanding on average. So anything that we are able to deduce about this definition will give us a C1 open set where something sort of pleasant will be happening, whatever that pleasant thing we manage to deduce is. So one more thing I want to note is that kind of as Davi pointed out yesterday, like we're not assuming that any of the random dynamics we're applying, we're not assuming that any particular map in the random dynamics is like an expanding map or an Anosov diffeomorphism or something. So the kind of random dynamics we're considering is really like non-uniformly hyperbolic. If you want to think about it really in terms of non-uniform hyperbolicity, kind of in the course of studying random dynamics with this kind of condition, what you sort of, in some sense, can find out is that the random dynamics of expanding on average systems on surfaces look like you're studying like a Pessin set with like an exponential tail on the constants involved. That's kind of what the submartingale properties give you. So let me give you another example of a kind of different flavor satisfying this. So suppose F is some smooth diffeomorphism, for instance. The smoothness isn't really important. And F has finitely many periodic points of each order. And then let's just fix some epsilon not greater than 0. Then we can consider for a open and dense set of different piece of chalk. For an open and dense set of conservative vector fields, vector fields X, we can consider this random dynamic. So first, apply the diffeomorphism F, and then flow for a little tiny amount of time, where T is uniformly distributed on this interval. And so then this random dynamics, this is expanding on average. So if you start with some diffeomorphism and you add like basically any conservative flow you pick, and you're willing to flow for like a tiny random amount of time, it'll be expanding on average. So it doesn't take super huge noise in order to make this happen if you want to do it perturbatively. Now, okay, now I'm kind of maybe begging the question because I said, well, okay, here's some condition, now it has some properties, here's some examples, but I didn't tell you like anything that actually follows from this. So let me now tell you some properties. So maybe you can feel like it's a little more interesting. So one of the first things that was noticed is that, so these are properties just for surfaces. Just talking about surfaces still. So the first thing is that expanding on average, maybe I'll say properties of expanding on average for surfaces. So the first thing is ergodicity. And this was essentially proved by Olga-Piat and Krikorian in 2007. And what do I mean by ergodicity for a random system? What I mean is that there are no positive, intermediate measure almost surely invariant sets. So if you're familiar with random systems, then you know this. If you're not, most of the concepts from ergodic theory for deterministic dynamics basically transfer right over to the random setting with like as few modifications as possible is usually the right analog. So they showed expanding on average for surfaces ergodic. I mean, they showed more than that in the paper, but I'm just talking about surfaces. In particular, also, if there's a paper by Brian Chung that I think explains this argument kind of more in this language. They don't really state it this way in the paper. So first, you get ergodicity from this criterion. So what we know now is that C1 perturbations, small perturbations of this, for example, are ergodic with respect to volume. Okay? So then later, large deviations were studied by C. Liu in, I think, like 2016. And then measure classification, as Davi mentioned. I mean, many of these papers prove more things than just what I'm saying, but I'm just, it was proved by Brown and Rodriguez-Hertz in 17, and what they showed is that if you have any stationary measure for a system like this, well, actually then, it's not just a stationary measure, it's an invariant measure, and all the invariant measures are either volume or atomic. Sorry, I didn't say what a stationary measure is. So a measure, so let me just say station. So say nu is stationary. This isn't my focus. Mu is stationary if its average push forward is itself. If nu is equal to the expectation of, so it's like harmonic for the dynamics. And so what they showed is all the stationary measures are actually like kind of the invariant ones, and all the invariant ones are kind of the obvious invariant ones. So, which is pretty strong. And then, I guess as we saw yesterday, so when you perturb out of this conservative setting, there exists an absolutely continuous stationary measure. Okay, I won't repeat the hypotheses Davi said yesterday, but I just want to remind you that this was proved. It was proved by Brown, Lee, Obata, and Ron. Okay, so this condition, it gives many good properties. And in fact, there's sort of a conjecture from this original paper where they saw that it was ergodic that says, if you look at the pairs of diffeomorphisms preserving volume, then an open and dense set should be is expanding on average. And they don't state the conjecture quite like this in the paper where they prove this, but they say stable ergodicity should be dense, open and dense for random dynamics. And kind of, when you read the paper, you see that they're kind of telling you that maybe this is the reason why. Okay, so now I've kind of laid it out for you. Now, if you're not super interested in random dynamics, there's sort of other reasons why you might be interested in this. Well, one reason is that, oh, sorry? Oh, sorry. Sorry, I should say for the measure delta F. Sorry, so choose F and G with equal probability, then it should be, sorry, I should have said that. Yeah, so you have the space of pairs, and it says if you take a pair and you choose the random dynamics that applies one or the other with equal probability, then that guy should be expanding on average. Yeah, sorry, I should have said that. So maybe one way you might get to studying these random systems, even if you had no interest in random dynamics to begin with, is if you're just studying some group action on a manifold, though there's no reason there would be any common invariant measure, for instance. And so it becomes very quickly you can find out that like if you're willing to study the random dynamics and the stationary measures, then actually you can learn a lot maybe about what's acting, even though you didn't really start from anything. Another reason that I think is my own motivation for being interested in the conjecture is, what if the conjecture wasn't true? Well, it would basically mean that stable ergodicity is not dense in the space of pairs, which would tell you that there was probably some kind of random version of like the KAM phenomenon that's happening that's stopping you from perturbing things to make them ergodic, which I think would be very surprising given that you have two maps, and it would basically be like, I don't know how it would look. You'd have some weird simultaneous like KM torus or something, which I think seems like not like something that should be happening. Okay, so now I've told you about all stuff that other people proved, and now I want to tell you just about the first result.
Question for the conjecture, is it like M is a...
Oh yeah, so they conjecture for any dimension. Yeah. Yeah, the conjecture stated in the paper is not quite stated like this. It says, what they say is, for any dimension, there exists a number like 2 for that dimension, so that if you look at all the tuples of length m, where m depends on the dimension, then you have this. Then you have stable ergodicity of the tuple. So I'm like, I don't know, editing it a little bit to, because I mean, when you read the paper, it's kind of like they're telling you to check this. I don't know, that's how it felt to me anyway. Okay, so now, I don't know how to prove the conjecture. I mean, one thing I should say is that because this condition is like C1 open, if you have some explicit 5 diffeomorphisms, and you're able to communicate to the computer your 5 diffeomorphisms, you can have it check. And in the paper of Chung I mentioned before, he kind of shows you how you could do that. So in principle, it's checkable. And there are a number of other examples that are known, like Cantat and Desjardins have examples of some algebraic systems where they use it to great effect, and Potry and Elliott-Smith showed like a weak star density of this condition, so there are a number of examples. So anyway, here's the first theorem I want to talk about. So I'm just going to tell you what the theorem is. So it says, by me and Dima, 4. So the theorem says, conservative, expanding on average, mu on the surface is quenched exponentially mixing. Now, in case you're not familiar with what I mean by this, let me tell you what this literally means. What this means is that for any alpha greater than 0, which is some amount of regularity, like a Holder regularity, there exists some constant eta greater than 0, which is going to be an exponential rate of decay, such that for mu, almost every choice of the random dynamics omega, what do you get? Well, if you look at two functions, phi and psi, on the manifold, you compose one with the dynamics, you integrate against volume. Well, this is going to converge to what you would have expected if they'd just been like completely independent of each other. So it'll converge at some rate that depends on the choice of the random dynamics omega. The exponential rate doesn't depend, but this constant does, times the Holder constants involved. Because if you start with some more irregular functions you're trying to mix, you have to pay, and it's going to take you longer to mix. Sorry, so these are supposed to be on the same line. I just didn't erase. So does this statement make sense? This is like, so when I say quenched, it means that for almost every specific realization of the system, there's no averaging over the dynamics here. It just says you pick almost every choice of the random dynamics, and it's going to mix the two functions up. Okay, so now I just want to say one word about what the proof of this is like, and then I'll move on to the next thing. So the proof of this theorem is like kind of classical in flavor, I guess. So proof is a coupling argument.
So by conservative, you mean they're all error preserving?
Oh, yes, yes. Oh, yeah. Sorry, I should have. Yes, yeah, they're all area preserving, and the argument kind of works if you leave area preserving just a little bit, like the estimates that you need still survive, but we didn't write it that way. And the argument itself is a coupling argument, and what that means is, you have two curves in your system, and what you want to do is, if they come close, to see that many points on the first curve will get coupled, to many points on the second curve by using the stable manifolds of the random dynamics. And so it's kind of technical, but it uses standard pairs. And probably a good, a place where this kind of argument is explained is, also is in the book of like Chernov and Markarian, but it also uses a lot of like Pessin theory. And so much of the paper is dedicated to like building this kind of version of, all the estimates from Pessin theory to make use of the estimate so that you have all the exponential tails you'd need to carry out this argument. Let me just say one more thing. Actually, this proves something stronger than this. It proves that if you just had a function defined along a curve, then that would mix into the manifold. And that's a lot kind of more delicate than knowing that volume itself mixes. So it also says curves mix. Is a byproduct of using standard pairs. To prove it, you find out that actually curves mix. So that's all I want to say about surfaces. So is that okay? Oh.
Don't you need some depending on average? Could you not have a situation like that where you have delta F plus delta G, but F and G? Oh, I see. So it's included in that they're not kind of going against.
Yeah. You're right. So I think this condition is kind of a fussy one to swallow because it's one good thing about the expanding on average condition is you can characterize it in terms of the existence of certain like almost surely invariant measurable structures that live inside the tangent bundle. And so it's kind of checkable because sometimes you can kill them all off, which is kind of how the argument for this works. So now I want to talk about, I'm going slower than I thought. What about higher dimensions? So, okay, that's what, so we worked in dimension 2, and then we were interested, what can we say in higher dimensions? So one thing I want to note is that, so what's a good thing about this condition in higher dimensions? Well, if mu is expanding on average, then the two-point motion of mu is expanding on average. And what I mean by that is consider M cross M and act on it by the diagonal. This is like seeing how a pair of points in the system is evolving in time. So that's a good thing because often, ergodic properties and stuff you want for a system like this have a lot to do with the stuff here. So that's nice, and maybe is reassuring. The bad news, though, is that you can't prove anything. So, oh, no, it's all right.
The expanding on average definition says
Yeah,
in every direction.
yes.
Here's some examples, but so if you take two and also, will their average?
I think as long as they're not like A and A inverse or like powers of each other, then I think it should, I mean, if they're like linear ones, then that should be true. But
You need the expansion in every direction.
yeah, so it's kind of like, for two and non-sub diffeomorphisms, they're kind of going to be expanding on average as long as like one of them doesn't preserve the stable bundle of the other one. So as long as that doesn't happen, then you're kind of good. If it does preserve the stable bundle of the other one, then, well, you're kind of out of luck because now the direction inside the stable bundle, one of them just shrinks it, and then the other one like can't help, basically. So if you met, yeah, for instance, so, yeah, because kind of the enemy when you're trying to check this condition is basically that there might be some like line bundle or something that everyone is preserving. And for the vectors living inside that line bundle, you have no estimates, basically, because you're at the whim of the diffeomorphisms. Whereas if you don't, you're more like in Furstenberg's theorem, kind of, or something. Okay. So in higher dimensions now, what's wrong? Why can't we just be happy with the condition we had? So expanding on average doesn't even imply ergodic. Actually, it doesn't imply anything, basically. You can give examples of expanding on average systems in dimension 4 that like fiber over the identity, basically. Like, so they could have like no ergodic properties at all. So not good in higher dimensions. So now I want to tell you what I think is a reasonable alternative. So here's my new definition for you. So this is for higher dimensions. So we'll say probability measure mu on diff infinity vol volume preserving of M is co-expanding on average. If there exists, just as before, some constants n and c greater than 0, so that for all x in M and any unit tangent vector z, unit cotangent vector, this is my unit cotangent bundle, T star 1, we have the same estimate. So the expectation over the nth power of the dynamics of n inverse the log df star inverse. So this is like the push forward of this cotangent vector by the dynamics is greater than or equal to c, greater than 0. So, okay, so that's the definition, and you can look at it for a second. The reason I wrote it this way is that basically this is kind of looks very similar, right? Except now the middle part's kind of messed up. The way I think about this is like like cotangent vectors normally pull back by the dynamics. So I'm just going to push them forward so that it's a cocycle over the forward dynamics rather than the reverse. And what this says is if you take your unit cotangent vector and you push it forward n times, then the expected length is long, typically. And so this is the definition. Now, if you want to be super concrete, and you had some linear map A of the torus, then what you'd be getting here, if you use the usual identification of the tangent and cotangent bundle on like flat torus, you had a linear map A, then this would be like A inverse transpose, is what it would be very concretely. So cotangent vectors grow, and when pushed forward. And so now I want to tell you a result under this condition. So in order to do that, I want to just introduce two more pieces of notation. So first, let me consider hs of m. So where S is in R. These are the usual Sobolev spaces, the Hilbertian ones. That's why I wrote H, they're Prague spaces. And also write G acts on a function phi by just pulling it back by the dynamics. So this is the usual like generator of the action on functions. And now here's the theorem, and after I tell you the theorem, I want to tell you about some other previous works. So me and Dima. 25. So suppose that mu is co-expanding on average. Then there exists S naught greater than 0, such that for S in some tiny little interval around 0, or near one-sided interval near 0, the action of this generator on HS has an essential spectral radius less than 1. And if mu inverse is co-expanding on average, then the same holds for the G acting on negative regularity functions. So small negative regularity. Okay, so there's the statement. It says, suppose you're willing to assume that very technical looking condition over there. Then when you look at how we act on functions, you actually have essential spectral gaps. So what that means is when you look in the spectrum of your operator, there's some place where like most of the spectrum is. This is like the essential spectral radius. And then there's like an edge to it, the essential spectral radius. And then outside that, there's just like a finite amount of stuff. So this is what essential spectral gap means. So what else did I want to say? So one thing I should emphasize is that essential spectral gap doesn't tell you anything about ergodicity, for example. Like you can have your random dynamics have essential spectral gap, but maybe 1 is a very, very high multiplicity eigenvalue or something. Well, how could you be ergodic if that was the case, for instance? So it can't tell you something about that. So the idea of the proof is kind of like this condition looks a lot like how an expanding map would look. So it makes sense that you could use some kind of microlocal stuff in order to analyze it. So there are other works that have pursued, I think, a similar approach. So I want to draw your attention in particular to 2, which studied something similar in a kind of different context. So So the first thing I want to mention is work by Tsuji. Masato studied a kind of related condition called virtually expanding for endomorphisms. And then by applying a microlocal approach where essentially you look at, well, I'll show you in a second, you kind of look at the kind of operator that knows about Sobolev regularity, and you see that this condition, or kind of related condition that works for endomorphisms or makes sense for them, kind of is very compatible with that. Also, another paper that's, I think, pursues a similar kind of approaches by Bedrosian, Flynn, and Punchen-Smith in 24. They also sort of, so this argument kind of works directly by looking at the action on the operator Laplacian to the minus s. And so this paper studied sort of random diffeomorphisms under some kind of hypothesis on the continuity of the stationary measure of the projective process. And so like if it was absolutely continuous, that they can similarly study the symbol. And so like these two works, I think, similarly, like to what I'll tell you in a minute, studied this. I should really emphasize like Masato has studied, you know, he proved many things about endomorphisms, and like as you saw in Davi's talk mentioning the application of the transversality argument, like these ideas I think are pretty good also for the random stuff, because and the random stuff I think is a little more flexible in some ways too maybe. So anyway, what did I want to say? So the next thing I actually want to say is a corollary of this that I find kind of, I don't know, I was kind of surprised by it when we proved it. So suppose that you know that mu and mu inverse are co-expanding on average. Then as before, there's some S naught greater than 0, such that, oh yeah, sorry. So this is like the push forward of mu by the map F goes to F inverse. So this is like the forward dynamics, and this is the backwards dynamics. So if you know that both of these are co-expanding on average, then G has essential spectral gap on HS for S in minus S naught, S naught. And in particular, it has spectral gap on L2. So, well, essential spectral gap on L2. And so somehow like if you're only, somehow the argument itself never sees any L2 stuff. But if you know that you have spectral gap on HS and H minus S, then you can use sort of, I don't know, a very useful fact, which is that Sobolev spaces are interpolation spaces. So if you have an operator that's sort of acting on H minus 1 and is also acting on H1, then it's going to act on the interpolated spaces between H minus 1 and 1, in particular L2. And the facts about the spectral radius of G from those spaces that you interpolated from imply strong things about the space that you're interpolating onto. So this is a corollary basically just by interpolation. So the fact that I'm telling you is that complex interpolation of Sobolev spaces gives you Sobolev spaces. If you use real interpolation, you'd get some fact about Bessel spaces, I guess. I don't know why you'd want that or not. So let me just tell you like a particular application, which was like, actually for me, like the reason I was studying all of this in the first place. So here's some other corollary, well, of some other work too. Suppose R1 through Rm generate a dense subgroup of SO2D plus 1, right? Well, then those act on S2D. They act on a 2D dimensional sphere, even dimensional sphere. Well, if I take them and I perturb them, so take some C infinity small perturbation. Well, now this perturbation is going to have some strong properties. In fact, it'll satisfy a dichotomy. So it'll be co-expanding on average, both forwards and backwards. It'll be exponentially mixing, have the CL central limit theorem, and it'll have L2 spectral gap, for instance. Or it'll be simultaneously conjugated to rotations smoothly. So it couldn't have those properties, or it couldn't have some of them. Right? Yes, it's exponentially mixed. It is ergodic, it is ergodic. Yeah, because it's even. Yeah. Yeah. Exactly. Sorry. So this is like a corollary of the thing over there, and yeah, the Dolgopek-Krikorian's paper where they showed the same alternative, except the first thing in the alternative was like it is ergodic, but sort of in what they really show in the paper is that it's okay. They don't say it exactly, but if you read the paper very carefully, you see that actually what they proved is this. And so then you can feed it in. So let me just add another remark is like in my thesis, I studied like this same result, but for isometries of isotropic manifolds. And so what this stuff all shows in that case is that a generic perturbation will have all these properties, even if you perturb isometries of like CP7 or something. But the ergodicity is kind of the hard part. So, okay, now I went a little slower than I should have. I think that the part that needs to be generic is actually pretty low regularity. Well, no, in C infinity is okay. Well, I think like it's really like an open and dense set, basically, in whichever topology. Yeah. Okay. Well, yes. But I mean, like the problem in like for CP7 is that it's very hard to tell even if the perturbation is co-expanding on average that it's ergodic. So you have to do like one extra little perturbation to like kill off the extra ergodic component. So it's kind of a consequence of the stuff over there. Knowing that you have the essential spectral gap basically shows you have finitely many ergodic components. So now it's kind of easy to like, to get rid of them. And then you have the ergodicity. So okay, maybe I have not very long, but so as I said, this is some kind of, microlocal argument. So what do I mean? So what do I want to say? How can I abridge it? So basically, how can you study Sobolev regularity? Well, you can do it using a pseudo-differential operator like this. And you can say, if you have your function phi, the H minus S norm of phi is like this. So the way you should think of this operator, this like Laplacian to the minus S, is just think about like Fourier series on a torus. Right? The way you could define Sobolev spaces is by assigning like a weight to each one of the modes of the Laplacian, and you can penalize it for being higher and higher frequency. right? For positive regularity Sobolev spaces, you say it costs you more to have very high modes. You say, if your eigenvalue is like lambda, I'm going to charge you lambda to the 100 in norm, and that would be like H100 or something. For negative regularity Sobolev spaces, you do the opposite. You say, well, it's okay to have very high norm because you're going to pair really well with smooth functions if you're high norm, because smooth functions, if you integrate something really wiggly against them, it all cancels. So one way you can encode this is you can cook up an operator called this negative Laplacian, and its symbol, which is a map from P star m to r, basically looks like this. So if you have some unit tangent vector, then the symbol looks like this. And basically the way you could think about this is it says if you zoom in really close and think about this picture from the torus where you're like penalizing higher modes more or less, it's saying when you look at higher frequencies, when you've zoomed in really close, penalize them a lot less. Like, it's okay to be high frequency. So, oh, sorry. Yeah. Wait, say again? Sorry, so I should say, so if you assume mu has the property, then you get positive S. If you assume mu inverse has the property, then because it's like the adjoint of this one, then you get negative S. So it's, yeah, they're kind of like the same statement, I guess. So then kind of the way the argument works is like you're interested in knowing about this. You want to know about the Sobolev norm of, like, you apply this. You're interested in this. And what you can check is that if you push this thing through, this kind of looks like the integral of right? And now this is some L2 thing, right? So if you apply another inequality, you can break it up into pieces. Oh, okay, yeah, sorry. You can break it up into pieces like this. I just want to give some indication of the proof, just because I think it's. And now this is an L2 norm. This is, you push your function forward and applied this operator. Now you can just translate it back by applying f. F is an isometry on L2 because it's volume preserving. So this is exactly the same thing as the integral of pulling back the operator to where you started. And so basically now what you end up doing is you see this kind of looks like some new operator. Like if you averaged all of these things, this isn't literally what happens. You pull back the operators and you average them. Now you can compare the symbol of this operator, where you've averaged by the dynamics, with the symbol of the operator you started with, like this. And if you work through what this condition says, it'll tell you that this one's symbol is a lot smaller than that one's symbol. And so you can compare the actual size that the operators will have on functions, basically because their difference is an elliptic operator. So okay, now I'm over time to FCC. Sorry, thank you.
Any questions?
So do you require any kind of integrability of your initial measure? So you are assuming compact support?
Oh, that's, yeah, so everything I've written is all for compactly supported, but I think maybe it could be okay with it, yeah.
Excuse me, regarding the conjecture you mentioned about typicality of this condition EOA, you always assume that the weights are 1/2, 1/2. But if you change this to P1 minus P, do you think that these are the same in an open and dense set?
I think for a given choice of weights, there should be an open and dense set, although if you do change the weights, it might stop being expanding on average. If it was expanding on average for like a good reason, then it won't affect anything, but if it was kind of expanding on average by accident because it lined up in just the right way and the weights allowed it to be expanding even though it was a common shared direction. So like I think for any particular choice of weights, it should be that there's an open and dense set for that weight.
So generically, you
Yeah.
think they are the same?
Yeah.
Any question?
Just a small comment that perhaps your history goes a bit more backwards in time. Like if you think of the classical context of non-commuting products of matrices, people like Lepage, Bougerolles showed that this kind of expansion of average implied the spectral gap property and everything else. Well, the space of observables is different, but it's the same kind of principle. On projective space, yes.
Yeah.
Okay, so there's no more problem, so thanks the speaker again.
Hi, just another logistic announcement as my role. So the next few talks are 2 parallel sessions, right? And so